Last time we saw that we could use polynomial time reductions to compare the difficulty of different decision problems, and that reductions let us make those comparisons even between problems that we don't necessarily know how to efficiently solve. This time, our goal is to go beyond comparing individual problems and start establishing a system for classifying the difficulty of any problem. To do this, we will define two broad classes of problems. P is the set of all problems that can be solved in polynomial time, and NP is the set of all problems that can be verified in polynomial time. To distinguish between these classes of problems, we need to establish precise definitions for what we mean to solve or to verify a given problem. When we say that a decision problem belongs to the class P, we are saying that there is some polynomial time algorithm that correctly solves that problem. So to prove that a problem is in the set P, we have to provide an algorithm for it, and then prove that the algorithm runs in polynomial time, and that it correctly solves the problem. And of course, proving the correctness of an algorithm for a decision problem means proving that the algorithm outputs yes, if and only if it was given a yes instance of the problem. And this approach of specifying an algorithm, analyzing its running time, and proving its correctness is the sort of thing we've been doing all semester. It's just being applied here specifically to decision problems. The part of this classification that is a much bigger departure is NP. NP is the set of all decision problems for which we can efficiently verify a solution. And the key idea is that for any yes instance of the problem, there is some way to prove that that is in fact a yes instance, and we can write an algorithm that checks that proof in polynomial time. It may or may not be easy to come up with that proof, but once we have it, we can check it efficiently. So in our formal definition, the way to prove that a problem belongs to the set NP is to show both a verifier algorithm and a type of certificate for that problem. These certificates correspond to instances of the problem. So for any given instance, we might have a certificate, and the certificate is supposed to help to show that the answer on that particular instance is yes. The job of the verifier is to check that, in fact, we have a valid certificate showing that the answer was yes, and we want this verification process to take polynomial time. So we require that the verifier be a polynomial time algorithm, and also that the length of the certificate be polynomial with respect to the length of the original problem. So proving membership in NP means describing how to come up with a certificate for any given yes instance of the problem, and showing that the verifier, when given a yes instance and a valid certificate, outputs yes, or if it's given either a no instance or an invalid certificate, it will output no. This definition has a lot of moving pieces, so I think it will make a lot more sense if we can see it applied to some familiar examples. If we want to show that the independent set problem is an element of NP, then we need to give a certificate and a verifier and prove properties 1 through 4. And remember that the job of the certificate is to serve as a proof that a particular instance of the problem is a yes instance. So for independent set, our problem instances consist of an undirected graph and a size of independent set that we are looking for. So given a particular graph and set size, if we want to prove that the answer on that input is yes, we could write down an independent set of the appropriate size. Remember, we don't yet have an efficient algorithm for finding independent sets, but Our goal here isn't actually to solve the problem. Our goal is to show that if the answer is yes, there exists some way to prove it. And so if the answer is yes, there should be an independent set, and if somebody gave that set to us, we could check that it is in fact an independent set in the graph. So our verifier would need to check that the set we are given is in fact a subset of the vertices, and that the size of the independent set is at least k, and that the set we were given is in fact an independent set, meaning that for every pair of vertices we were given, there's no edge between them in the graph. So, for this proposed certificate and verifier algorithm, we can ask, does it meet all of the criteria? Is it the case that whenever the answer on the problem was yes, there is a certificate? Well, yes. If the answer was yes, then the graph has some independent set of size k, and so we could write down that set as a certificate. Is it the case that the certificate always has polynomial length? Well, yes, because we were given all of the vertices and edges of the graph as input. Listing a subset of the vertices takes less space than the original input, so it's definitely polynomial. Does our verifier algorithm run in polynomial time? Well, we have to check that everything we were given is an element of the vertex set. We can definitely do that in n² time. We can check that the size of the vertex set is at least k. That should be constant time. And we can check that for every pair of vertices, there's no such edge in the graph. And we should be able to do that in n² time. So all of those operations take polynomial time, so our verifier algorithm is polynomial. And we need to show that our verifier will output yes if and only if it was given a yes instance and a valid certificate for that instance. Well, what if it was given a no instance? Well, for a no instance of this problem, that would be a graph that has no size k independent set, which means that for any certificate we might give, it's going to fail one of these checks. Either we didn't give enough elements, or some of those elements weren't independent, or we tried to cheat and gave a collection of elements that wasn't actually a subset of the vertices. But what if we gave a yes instance with a valid certificate? Well, that valid certificate would be an actual independent set, and so that independent set would pass all of these checks, and we would output yes. Or what if we gave a yes instance and an invalid certificate? Well, an invalid certificate would be not an independent set of size k in the graph, and so it would fail one of these checks because either it's not a subset of the vertices, or the vertices are not independent, or the size of the set is too small. So our verifier will output yes if and only if it's given a yes instance and a certificate proving that that was a yes instance. And so we've just argued that independent set is a member of the class NP. And this gives us a blueprint for providing certificates and verifiers for all these other problems. Namely, if the problem is asking whether a thing exists, provide an instance of that thing as the certificate, and write a verifier that checks that we've given a valid instance. So for the vertex cover problem, we could give a listing of all of the vertices in the vertex cover, and then our verifier would need to check that we have, in fact, given a subset of the vertices that is of appropriate size, and that meets the criteria of a vertex cover. Our verifier for vertex cover checks that we have given a subset of the vertices, that the size of that subset is less than or equal to k, and for every edge in the graph, we have one end or the other of that edge in our vertex cover. So if we have a yes instance of the vertex cover problem, then that is a graph where there exists a size k vertex cover, and so a certificate would exist. Our certificate is a subset of the vertices, so it has polynomial length. The checks run by our verifier all take polynomial time, and we output yes if and only if we are given a yes instance of the problem and a certificate proving that that was a yes instance of the problem, because if we are given an invalid certificate, it will fail one of these checks, and if we are given a no instance, then there cannot be a valid certificate, so again, one of the checks must fail. And so independent set belongs to the class NP. Likewise, for set cover, our certificate proving that the answer is yes could be the collection of subsets that has appropriate size and covers all the elements. And our verifier needs to check that the thing we have given is in fact a set cover of appropriate size. Our verifier needs to check that in fact we have given a collection of subsets from those that we were given, and that the number of sets we have chosen is at most k, and that when we union together all of the sets that were chosen in our set cover certificate, we get the entire set U. So, for any yes instance of the set cover problem, there must exist a way to pick k of the sets and cover the entire universe. So for a yes instance, there exists a certificate. The certificate has to list out which of the subsets we are picking, but that is smaller than the original problem size and is therefore definitely polynomial. Our verifier algorithm runs through these checks, but each of those takes polynomial time with respect to the problem size. And our verifier will output yes if and only if it was given a yes instance and a valid certificate, because these checks ensure that T is in fact a set cover of size less than or equal to k, and so we will output yes when we are given a set cover for the given instance. But if we are given an invalid certificate, then either we don't cover everything, or we have too many sets, or we were not actually picking valid subsets. And so an invalid certificate would fail one of these checks. And if the problem instance had the answer no, there cannot exist a valid certificate, so we will definitely output no whenever we are given a no instance and any certificate. For the decision version of the minimum spanning tree problem, we were given a graph with weights, and we were given a threshold where we were asking, is there a spanning tree with weight less than or equal to this threshold? And so our certificate could be a spanning tree of the graph that meets our threshold criterion. To verify the certificate, we would need to check that the thing we were given was actually a spanning tree, which we can do by counting the edges and ensuring that the graph is connected when restricted to those edges. And that when we sum up the weight of all the edges in that spanning tree, it is less than or equal to the threshold k. So for any instance of our minimum spanning tree decision problem, if the answer is yes, then there is some spanning tree with total weight less than or equal to k, And so we can give that spanning tree's edges as the certificate. That certificate is a subset of the edges, so its length is less than the original problem and definitely polynomial. Our verifier has to check the size of our set and that it is a subset of the edges. Those definitely take polynomial time. Then it has to check that we actually have spanned the graph, which we can do by breadth first search and ensuring that all of the vertices are visited. And we know breadth first search takes polynomial time. And then we have to add up the weight of all of the edges in the set, which is again polynomial. So our verifier overall takes polynomial time. And if we are given an instance of the problem and a purported certificate, is there any way that certificate could fool us? Well, no, because the certificate has to give us a subset of the edges that has the right size and spans the graph, and we check that those edges have total weight less than or equal to the threshold. So if there's anything wrong with the certificate, we will output no. But if we're given a yes instance and a valid certificate, we'll output yes. And so our verifier operates correctly. And we've shown that the decision version of the minimum spanning tree problem belongs to NP. What about the max flow problem? Well, for the decision version of this problem, we are asking, is there a flow of value at least k? And so our certificate could be to provide such a flow. And here the job of our verifier is to check that we have given a valid flow, which means that the flow must map the set of edges to natural numbers. And the thing that we are claiming in this certificate is a flow also satisfies all of the capacity constraints, being between 0 and capacity for every edge, as well as all of the conservation constraints, having inflow and outflow equal for all edges except for S and T. And we have to check that the value of the flow is at least k, which we can do by adding up the flow on all of the out edges of the source. If we are given an instance of the max flow decision problem where the answer should be yes, then that means that a flow of value at least k exists in that graph. And so, for any yes instance, a certificate should exist. The certificate has to specify the flow on every edge, but that has size big O of number of edges, and so that's linear with respect to our original problem input. Our verifier has to check the inputs and outputs of the mapping, which takes linear time. It has to check all of the capacity constraints, which means checking the flow on every edge, so that's linear time. And checking all of the conservation constraints, which means adding up the flows into and out of every vertex, but that will overall take n plus m time. And adding up the outflows from the source will take big O of n time. So overall, we have a polynomial time verifier algorithm. And our verifier will output no if the thing that is given is not a valid flow, or if the value of that flow is not at least the threshold. So we will output yes if and only if we are given a yes instance and a corresponding certificate. And so we have shown that all of these problems are members of the class NP. Specifically, for these last two problems, we know how to solve them in polynomial time. Because we have a polynomial time algorithm for finding a minimum spanning tree or finding a max flow, we could answer the decision version of the problem by running that algorithm and then just checking whether the threshold was met. And so because these two problems that belong to the class P also belong to NP, a valid question to ask is, how do the sets P and NP compare? And we can start to answer that question by proving that P is a subset of NP, which means that every problem that can be solved in polynomial time is also a problem that can be verified in polynomial time. To prove that P is a subset of NP, we need to show that any problem in P is also in NP. But if we have a problem that belongs to the set P, then we know there is a polynomial time algorithm that solves it, and we can use that polynomial time algorithm to build a verifier. Specifically, our certificate can just be the word yes, and our verifier algorithm can simply check that the certificate is the word yes, and then run the algorithm that solves the problem on whatever problem instance we were given. So now we need to show that this verifier and the corresponding certificates meet all of our criteria for NP. First, we need to show that for any yes instance of the problem, there is a certificate, and we've chosen the same certificate every time, so we can just pick that certificate. And we need to show that that certificate has polynomial length, but its length is constant. And we need our verifier algorithm to run in polynomial time. But since our verifier algorithm just has to check that the certificate was yes, that takes constant time, and then it can run the algorithm f, but since we are talking about a problem that is in the set P, we know that our algorithm to solve it takes polynomial time. And for number 4, we need to show that our verifier will output yes if and only if it was given a yes instance of the problem and a valid certificate. Well, what if it was given an invalid certificate? Well, an invalid certificate would be anything other than the word yes, and our verifier would check that and output no. Okay, but what about cases where we are given the certificate yes? Well, then we run the algorithm f on the input that we were given, and so if that input was a yes instance of the problem, our verifier says yes, but if it was a no instance of the problem, our verifier says no. So really, we didn't need the certificate at all. We could just rely on the polynomial time algorithm to check whether a given problem instance was a yes instance or a no instance, and that by itself ensures that our verifier will output yes if and only if it was given a yes instance and a valid certificate. So this means that for any problem that is solvable in polynomial time, it is also verifiable in polynomial time. And that gives us a different way that we could have chosen our certificate and verifier for these problems that we know how to solve in polynomial time. But our statement of what it means for a problem to be in NP just says there exists some polynomial time verifier with the appropriate behavior. And so it's fine if there are multiple possible polynomial time verifiers that could work for the same problem. Either this proof or this proof would be sufficient to show that the decision version of minimum spanning tree belongs in NP. So we've proven that P is a subset of NP, but we have not yet determined whether P is a strict subset of NP, in which case there would be some problems that are efficiently verifiable that are not efficiently solvable, or if these two sets are equal. And this leads us to the most famous open problem in computer science, which is the conjecture that P is not equal to NP. There is a lot of reason to believe that these sets are likely to be distinct, but we do not yet have a proof, despite this problem having been open for many decades. To wrap up today, it's worth taking a moment to talk about where the names of these classes come from. You've probably guessed by now that P stands for polynomial, because it is the set of all problems that we can solve in polynomial time. But the name NP comes from non-deterministic polynomial. The reason for that is something that you would get into in much greater detail if you took theory of computation. But for our purposes, we can think of the non-deterministic part of the name as supposing that we had some way to guess a valid certificate. If you had the ability to magically guess a valid certificate for any yes instance of an NP problem, then you could combine that non-deterministic guessing with the polynomial time verifier that checks the certificate and turn that into an algorithm for solving the problem, and that algorithm would consist of a non-deterministic guess and a polynomial time check, and so you would have a non-deterministic polynomial time algorithm for that particular NP problem.